Today's presentation is about some applications of comb penetration testing in oil sand, a geotechnical practice. So comb penetration testing, CPT, has become a widely used site investigation tool. The presenter will first briefly introduce the background of CPT. Then she will share its application in a few oil sand projects, including the evaluation of liquefaction potential, characterization of soil tailings, and monitoring of the compaction effort. For today's presentation, we have with us Dr. Assile Abou Diab. She is a geotechnical engineer at WSP. She completed her PhD in geotechnical engineering at the American University of Beirut in 2017. Her thesis focuses on soil reinforcement with fibers. In 2019, she moved to Canada, where she pursued a master in geotechnical engineering at the University of Alberta and joined WSP. She has been primarily involved in the design and monitoring of some soil science projects in Alberta. So please join me welcoming Dr. Assile.
Good morning, all. Thank you a lot for the introduction, and thank you for having me. I'm really very excited to be here today and share my experience. My colleague, Ying Zhang, who is a senior geotechnical engineer at WSP and a graduate of the University of Alberta with a Master's of Science, helped in putting this together. He's present there in person, so he'll be very glad to chat with you at the end. Before I start, I would like to acknowledge the contribution of the team member to the work on the case studies that I'll be presenting. So a shout out to Gord Pollock, Ayman Abu Said, Ying Zhang, Yvonne Q, and Vicky Zhang. Thank you a lot for all your efforts. In my presentation, I'll go through a bit of background on CPT, advantages, disadvantages, general applications, and then I'll focus on select applications of CPT in the oil sand geotechnical practice. So what is comb penetration testing, CPT? As we see here, a CPT is an electronic probe instrumented with transducers and load cells and is connected to a series of 1 meter hollow bars tube. The whole thing is pushed down the soil at a constant rate. And while it is pushed, it measures the axial force on the cone, the friction on the sleeve, the pore pressure on a transducer that's usually mounted behind the cone. And this data is transmitted directly to a computer on site. And then this data, the raw CPT data, is interpreted using a bunch of empirical correlations in order to evaluate the soil behavior and estimate some geotechnical parameters that are of use and interest to our design. It comes in a variety of dimensions. These two are the standard sizes, 10 centimeters squares and 15 centimeters squares. But depending on the applications, we might use larger cones like the 40 centimeter square here to push through hard soils, for example, or the mini cone here, the 2 centimeter squares, for applications like pushing through very thin layered soil, for example. Site exploration is an essential part to tackle any geotechnical engineering problem. In the conventional drilling and sampling approach, we would have some standard penetration testing, vein shear to test the strength of our clays, pressure meter for modulus, packer for permeability, and then if we want to measure the shear wave velocity, we'll do some cross-hole testing. We will also collect some samples and do some lab testing on them. Nowadays, CPT is more and more used. It's a direct push technology that allows the collection of many parameters that are independent of each other, and it allows continuous testing throughout the push. So CPT is used in conjunction and in parallel with the conventional drilling and sampling. And it's very variable because it will help to fill in the gaps in the data. Because as we know, from conventional drilling and sampling, we test like select locations or at select depths. With the CPT being able to provide a continuous profile, it will be a very good addition to have the full picture. But we shouldn't regard CPT as a total replacement of the conventional drilling and sampling. Together, we get the best results. a closer look here at our cones. So the three main measurements from a cone CPT test are the total cone tip resistance measured at the cone, the pore pressures, and the friction along the sleeve. But this tool is really very, very, very versatile. So by adding like a geophone here and with a surface seismic source, we can measure the shear wave velocity, and with more and more sensors, we can expand the applications of the CPT. For example, the gamma CPT is now used in order to estimate the density of the soil and the soil's content. A bit of history: it was first developed in the 1930s as a mechanical cone. The idea was to push a tube and measure the force that's required to do so. And then electronic cones were developed in the 1960s. And then after that, we got the pore pressure measurements, more reliable load cells and electronics. We can add sensors and expand the applications. Our cones are now more robust and they allow to test a wide range of soil types. And regarding the testing of like very soft clays and tailings, I'll focus a bit on this because it's relevant to our oil sand applications and like testing the tailings. We have the ball CPT and the T-bar that are more efficient to test very soft clays. It's because and tailings. It's because these the tailings and the soft clays, the strength is very low, so even a small noise would affect the results. So by having a larger contact area, we can obtain more accurate measurements. So just for reference, a ball CPT, the area is around 100 centimeters square compared to 10 centimeters square for the cone. So really much larger contact area and more accurate measurements. In addition, by using the ball and the T, we can obtain the remolded shear strength of our tailings or very soft clays just by cycling in and out the ball for many times, and then conducting the measurements, we'll be able to get the remolded shear strength. In addition, the data is collected digitally and also processed using commercial software, so very easy to handle data. More advantages of the CPT: it's quick. We can complete a 20-meter sampling in about half an hour, the rate of penetration being 2 centimeters per second. We can test soils that are really difficult to sample, like the loose sands. We can obtain instantaneous continuous profiling. It's versatile. We can add sensors, expand the applications. And we have a bunch of empirical correlations that are supported and backed by lots of documented case histories. And we can use them readily available to interpret our raw CPT data. And even this interpretation can be done automatically using commercial softwares, or you can, for example, develop your own Excel sheet for data interpretation. Some disadvantages is that there's no soil sample. You cannot obtain a physical sample to look at and test in the lab. And despite the advancements, the penetration is still restricted in gravel cemented layer, and sometimes in dense sand we hit a refusal. A CPT can be performed from a regular track. It can be performed from a track mounted. And here, at location where we have problem in the access, so a track mounted CPT would be a solution. We can perform CPT from an amphibious platform here for the application where we have soft soils like swamps or beaches or tailings projects. In order to test from top of the water, a barge, we can also mount our CPT on a barge. Even we can have completely unmanned robots and perform our CPTs from that platform and control them remotely. And this is very important for applications for testing the tails, for example, in oil sand, because sometimes reaching those locations is not safe. So as a safety precaution and measure, having those robots perform the CPT while the operator is in a remote area is really very beneficial for safety. CPT rigs have a drilling setup, as we can see here, an auger drilling rig mounted on a CPT system. So the CPT can go hand in hand with the conventional methods. We don't have a much larger cost associated with mobilization, demobilization. It can work as a one system. The CPT applications in geotechnical engineering are plenty. From soil profiling and identification and classification, we can complete the soil profiling and identification just by visual inspection of the CPT traces, or we can use the empirical soil behavioral type charts. Also, CPT can be used to delineate the potential liquefiable soils. CPT can also be used to interpret the soil parameters, and then we can use these soil parameters in our designs and models. Parameters like in situ state, strength, stiffness, consolidations, etc. Even the CPT raw data like the contact, resistance, and the sleeve friction can be used as direct input parameters for some geotechnical design of foundation, like the SCPC method for pile capacity. But for the aim of this presentation, I'll be focusing on some select all sand applications, and the highlighted or bolded applications are the one that I'll be touching base on. The first case study is from Pond 5. Pond 5 is here located in Fort McMurray, and this is a closer view, Pond 5. Just a bit of background. So when we say all sand, as the name explains, it's about a mixture of bitumen and sand. In Fort McMurray, this oil sand deposit is shallow, very close to the surface. Then it is feasible to go and mine it through open pit mining using frac and shovels. So, and after this oil sand is mined, it is crushed, and it goes through an extraction process. In the extraction process, it's mixed with the water, solvents, and some chemicals. And at the end of the extraction, we'll get two products: the bitumen that's being extracted, and we have tailings, which is a waste product. These tailings, they consist of water, sand, fines, the solvents, and the chemicals, and it's kind of fluid slurry. And this tailing waste material is being stored in ponds. So all these ponds here that you see are tailing ponds. Previously, they were also open mines. And then when mining is done and you have this depression in the topography, we come and use it to store our tailings. Pond 5 is one of these tailings ponds. These tailings are very, very challenging, because if you leave them just by themselves, it will take years and years, like decades, to consolidate and settle. So they really pose a challenge for reclamation. So here at Pond 5, the technology that is being used is to cover the tailings with a coke cover. The tailings at Pond 5 range anywhere from 1 meter to 50 meter thickness, so really a variable thickness and thick deposit of tailings. The idea was to come and cover the tailings and install vertical strip planes to accelerate the dewatering and consolidation of the tailings. Here a glance at the coke placement history at Pond 5. In 2009, you can see the pond full of tailings. All the tailings are exposed. In 2010, they started covering the pond with coke, as we can see here, through roads. So how is this done? They waited until the winter season, because we need thick ice to be able to come on top of the tailings. So during winter season, they come and they started by putting geomembranes and geogrids, and they anchored them to the nearby beaches and dikes into roads. The system of roads was very efficient, because it allowed the access to all the parts of the ponds, and it's kind of contained the tailings in between. So as we can see here, the roads were almost completed, and they started infilling the cells in between with geotextile and coke. So after the roads were completed, they came in and they put geotextile in the cells. They anchored them to the roads. And in 2012, As we can see here, most of the cells were covered. By 2017, all the pond was covered with 2 meters of coke. And then this 2 meter coke formed like a platform, and that platform was used to install vertical strip drains to accelerate the consolidation of the tailings below the cover. And after that, the coke cover has been raised many times. In 2021, the coke cover was 4 meters thick. And as we are talking now, it's being raised again from 4 meter to 6 meter thickness. More photo on covering pond 5. So during the winter season, they came and they placed the geomembrane and then the geogrid on top. After the geotextile were installed and anchored to the surrounding dikes and beaches, coke was dumped and spread. So what is coke again? So from the extraction process, we got the bitumen and the tailings. The tailings are deposited in the tailings pond. We have the bitumen, but the bitumen is thick, so it needs to go through another stage called upgrading in order to obtain this lighter oil, that's the commercial lighter oil. And in this process of upgrading, we obtain another byproduct called coke. Coke is about carbon black. It's lightweight and cohesionless, as you can see it here. So that material was spread on top of the geotextile to form a cover on top of the tailings. We can see here first the roads being completed, and after completing the roads, the cells were covered with geotextile and also covered with coke on top. Here showing the geotextile, the drainage system at the bottom of the coke. We also put some instrumentation to be able to monitor to monitor the deformations, and we can see also the coke being placed on top. More photos on the equipment working on coke placement. And after the first 2 meters of coke was completed, the platform was used to install vertical strip drains, as you can see here, and we can actually see the vertical strip drains producing some water already. And then the coke cover was raised. Here we can see the placement of the fourth 1 meter lift of coke. We have the grade control marker to check that our lift is being raised by 1 meter. We have the whole track dumping some coke, and then the dozers will come push and spread the water trap to control the dust and to aid in the compaction. Here I'll show a short video from the first 2 to 3 meters of coke that were placed on top of the geotextile along a road. So the video is of a truck driving on top of the initial few meters of coke on a road. So as we can see in this video, there is excessive deformation. You can see rotting, cracks, a big depression whenever the truck passes, and after the truck leaves, it kind of rebounds. So the 2-3 meters of coke, the initial 2-3 meters were not as rigid. It's like a floating cover on top of tailings, and it wasn't rigid enough. I will just play the video again. Now, I want you to compare what you are seeing here with a newer video, and this video shows now the coke cover being raised from 4 meters to 6 meters in thickness. So now as the coke cover gets thicker and thicker, it is more efficient at spreading the load from the equipment that are trafficking on the surface. So we are not seeing any deformation or cracks or rotting anymore. It's the coke cover is still floating on the tailings, but because it's thick now, it's really acts as a rigid foundation for the traffic. So I'll play a video here. We can see the whole truck dumping the coke. The dozer was spotting for it. And after dumping the coke, the dozer will push and spread it. We can see the surface smooth, clean, no cracks, no deformations, and another hot truck here driving with no deformations too. CPTs and ball CPTs were used extensively in this project. In this select application, we'll be focusing on the perimeter investigation of point 5. And here, CPTs and both CPTs were used as part of an investigation program to delineate the soil stratigraphy and characterize the tailing around the perimeter of the pond. You can see here in black, these dots are the test and sampling locations. So in addition to CPTs and both CPTs, we also took some samples and did some lab testing, showing a typical cross-section of the dam here. You can see the fill, tailings sand, the tailings, and the coke cover on top of the tailings. This is the final design, and this dark line shows the actual coke cover here. At the time of the perimeter investigation, it was at 4 meters thick. I'll be focusing on one CPT location, and this location is here, so it will cover a bit of the coke, tailings, and tailings sand. So here showing how we can use the CPT trace to visually identify the soil type. I'm showing here the contact resistance, so the resistance at the contact. Here next, we are showing the layers of the soil profile identified from the logs, from the actual samples. And this is kind of to compare them to the trace of the CPT that we are seeing. If we look at the contact resistance, we see a drop whenever we are moving from the coke to the tailings. So in tailings, the tip resistance is really low, and then it started picking up again as we go into the tailings sand. Also, if we look at the pore pressure, remember the pore pressure is measured using a transducer that's mounted behind the cone. So we can see that in the tailings layer, the pore pressure was greater than the hydrostatic, and then it drops back to the hydrostatic in the tailings sand. We see here like 3 blue dots, and these correspond to dissipation tests. So what is dissipation testing? Actually, when we are pushing the cone at any depth, we can stop and do the dissipation test, which is mainly waiting until the pore pressure reach an equilibrium. In sand, the equilibrium is reached quickly, but in finer material, we have to wait some time before we see an equilibrium in pore pressures. The idea from the dissipation test is that because as we are pushing the cone, we might induce some excess water pressure. So doing those dissipation tests and allowing the time for these excess pore pressures to dissipate, we can obtain more representative pore pressures for our soil profile. Now this is the same CPT location. I'm plotting it on the soil behavioral type chart. Just to explain a bit of background about this chart, it was developed by Robertson in 2016. There are other older versions of this chart, but I'll be focusing on the latest. On the x-axis, we have the friction ratio, which is the ratio of the sleeve friction to the contact resistance. On the y-axis, we have QTN, which is the normalized CPT penetration resistance. It's the contact resistance normalized to the overburden stress and taking into consideration different soil types. So actually, these 2 parameters are just obtained from empirical correlations that use the main readings, the 3 main readings of the CPT data. Now, if we look at this chart, we have IB. IB is a soil behavior index. It's also a parameter obtained through a correlation. And what it indicates is the soil type. So IB of 32 or greater means that the soil is sand-like. IB of 22 or less, the soil behaves clay-like. And in between is a transitional zone. We have also the CD line. It's contractive dilated boundary. So the points that fall above this line fall in the dilated zone, while those who plot below this line are contractive. Contractive means they are susceptible to liquefaction. So in this application, we are interested in our tailings stand to see where they plot. The tailings stand are marked with the gray dots. As we can see here, our gray dots fall on the contractive dilative boundary, and many of the data falls in the contracted zone. So just by looking at this SPT chart, we can come to the conclusion that much of our tailings sand is susceptible to liquefaction. But for sure, we can go and do more analysis. We're just showing kind of the full picture on the same CPT location. So this is the same CPT showing the contact resistance, the sleeve friction, and the pore pressures. These are the three main readings from the CPT. We can think of them as raw CPT data. Here, I'm showing some lab test results that we conducted at the samples that we retrieved from the same location. And I'm presenting this to showcase that although CPT is very important and provides valuable information, sometimes it cannot give the full picture. For example, in this specific application, we have the tailings covered with a coke cover and VSDs installed, and we want to monitor how these tailings are improving with time. And this is really very important for reclamation and decommissioning activities. And in order to be able to crack this improvement, we have to look at parameters like how the soils contents are evolving and the sand to fine ratio. It really gives a good indication about the status of our tailings. And we cannot obtain these parameters unless we go and obtain actual physical samples and test them in the lab. So here is a good example of how CPT and conventional approaches can give us the full picture. From these three main readings, we apply many empirical correlations to come up with these parameters that are important in order to evaluate the susceptibility of our sand to liquefaction. And also we apply another set of empirical correlations in order to evaluate the underlying shear strength of our tailings. I'll focus on these two in the next slides. So on liquefaction potential and strength parameter of the tailings sand. So whenever we have tailings sand that is susceptible to liquefaction, the C/P ratio, liquefied strength ratio, is a suitable way to represent the strength. Here on the y-axis, we can see the C/P ratio, and on the x-axis, we have the QT/NCS. QT/NCS is same as the normalized contact resistance that we are showing here, which is the contact normalized to the overburden stress, and taking into consideration the soil type. But here, it's corrected for the fines content because the QT/NCS is used to evaluate the liquefaction potential, and we know that the fines content affect the liquefaction potential. More fines content means less susceptibility, so this parameter is corrected for the fines content to be more representative of the liquefaction potential. So Robertson developed this correlation C/P in function of QT/NCS in order to represent the C/P ratio of sand-like soils with QT/NCS less than 80. So mainly points with QT/NCS less than 70 are contractive and the underlying strength covers the design. Between 70 and 80, we are in the transition zone, but still the underlying shear strength would cover the design. So the C/P ratio this equation would apply up to QT/NCS of 80. For QT/NCS greater than 80, the soil is dilative, so the drainage shear strength will govern the design, and we revert back using tangent phi. In clay-like soils, the liquefied and drained shear strength is the same as the remodeled and drained shear strength, because both occur at large strengths. If we are pushing a cone, the remodeled and drained shear strength would be the same as the sleeve friction because they involve large strengths. And if we are pushing a ball or a T-bar in very soft clay or in tailings, we would cycle the ball or the T-bar many times and then conduct a test again to assess the remodeled and drained shear strength of the clay material or clay-like soils. So going again to the liquefaction potential and strength parameter, looking at our CPT trace, this is the soil behavioral index IB. So as we've seen here, IB 32 or greater sand, less than 22 clay-like, and in between transitional. So here, with the help of this plot, we can identify our tailings sand with IB greater than 32. And then the QT-NCS between 70 and 80 means that the soil is transitional, less than 70 it's contractive, more than 80 it's dilative. So as we can see here for our tailings sand, where IB is greater than 32 and QT-NCS is less than 80, we go and apply Robertson correlation to evaluate the C/P ratio, and we can see here the data plot. This will be we use this data to evaluate our strength parameter, liquefied strength parameter for the tailings sand. Here showing the undrained shear strength of the tailings. So we have the peak and the residual. We are showing in blue the CPT, in green the volt CPT, and the red are the vein shear test, and we can see that they all plot nicely together, they match. But here there is a step in between. So the equation to estimate, the empirical equation to estimate the undrained shear strength from the CPT involves a parameter called N. If we go to the literature, there is a range of values for N for each type of soil. But in order to use an N value that's representative of our specific site conditions, it's very important to calibrate the both CPT or CPT data against some in situ tests. In this case, we calibrated them against the vein shears, which are here, the 3 plots that we see here. So here I'm showing on the y-axis the peak undrained shear strength from the vein shear, residual undrained shear strength from the vein shear, and on the x-axis the ball resistance. We tried many parameters, many values for the N, and we found that N value of 15 would be representative, and from where the good match between the data. Now, how are we using all of this for our geotechnical design? The same work that we have completed on one CPT, we completed on the rest of the CPTs, and then we plot the whole thing on one graph, and we run some statistical analysis. So based on statistics, we found that plotting here the C/P ratio from all CPT for elevation 1050 and above, the 20th percentile for C/P would be 0.07. So we came and applied that to our design. For elevations 1050 and below, the 20th percentile is C/P of 0.04. So we used that value in our analysis. We did the same statistics on the tailings and remolded undrained shear strength, and the 20th percentile for the remolded undrained shear strength of the tailings was 0.5 kPa, and that's what has been used in the analysis. So we come and refine our analysis to reflect those strength parameters. Now the next case study is Sand Dump 8. Sand Dump 8 is another oil sand project up in Fort McMurray. So it is here, and this is a zoomed in view to Sand Dump 8. A plan view showing Sand Dump 8. Sand Dump 8 is a tailing sand structure designed and constructed with a minimum pond. It is an upstream construction, and each lift is 5 meters thick. The rate of raising is 10 to 20 meters per year. The tailings are hydraulically deposited along the perimeter. The sand that settles in those cells near the discharge forms the containment, the shell of containment. And because the sand is providing the containment shell, it should be very well compacted to make sure that it's not liquefiable. So it is dozer track path to produce dilative sand. And in order to monitor the compaction effort and make sure that it meets the specification, we have a lot of QA/QC programs. First, we have a representative on site to do the checks and the site inspections, and then all the doses that are compacting the cells are mounted with GPS, so all the number of passes are monitored, and we also check if they covered the whole area. And in addition to that, we run, after each lift, we run a CPT program where we check the liquefaction susceptibility of the compacted zone, and the compacted zone is hatched here. Just showing you a couple of profiles to appreciate the structure. This is the east section here. So tailings are hydraulically placed here, and then the sand that's captured gets compacted to form here the shell of containment. So this is compacted sand, and there is a buttress here. As we can see, between April and September, there was 1 5-meter lift that was added in between. The structure sits now at 385 meters, and we have few more lifts to reach the final design elevation, which is here, the green line, and the elevation is around 405, the final elevation. So we still have few lifts to be added before the structure is completed. And this is another section west. Same story, the compacted sand here being discharged and compacted. And we are at 390 elevation, few more lifts to reach the 405. Just a bit of details on the sand placement, zoomed in view here. So that this is a cell, we construct a cell, and then the tailings are discharged in the cell. And upon discharge, the coarse tailing sand, they form the sand beach here, and they are compacted using dozers to establish a non-liquefiable zone. The remaining fine particles that are not captured in the compacted zone remain suspended with water and flow towards the pond, and then the tailings collected in the pond are pumped and transported to another pond. More photos. So here we are showing the tailings discharge inside the cell, and you can see here the dozer. The dozer would go spread the tailings sand and compact them, and this is how our sand looks after being compacted with the dozers. You can see all the dozer tracks. Here, like zoomed out view where we can see the dozers during active tailings placement. So after each lift, after each raise, we do a CPT program. Up to date, there have been 32 CPT investigations. If you look at the plan here, the red dots are the CPT from the latest program, and the black dots are from older programs, and the blue dots are like from locations where we had many CPT along the years. So many CPTs at the same location throughout the years. And the majority of these CPTs were pushed down to refusal depth. Whenever we propose a CPT in the compacted zone, we make sure it covers the whole area, the whole compacted zone, but more specifically, we target locations with low dozer traces or where we have previously ponded water, and also new locations where we previously identified a liquefiable sand layer from old CPT programs. So how do we assess the potential liquefiable zones in the compacted tailings sand? We go through many steps to complete this exercise. The first step is we look at each CPT trace individually, and we assess the liquefaction susceptibility at each CPT location. So if we find at a certain CPT location that there is a liquefiable layer, we go and look around to assess the continuity of this potential liquefiable zone. Is it continuous throughout a specified area, or it's just like an isolated location where we have found that it's liquefiable? And the next step would be to revisit the continuity of potential liquefiable zone that were identified in the previous program, and just monitor and check, does this liquefiable zone persist in the new program, or they were dissolved? After doing step 1 to 3, there will still have potential liquefiable sand that extend to a considerable zone. Then we would go and examine the continuity of the potential liquefiable zones in larger area, on larger areas. So now we go and widen our area and check the continuity of the potential liquefiable sand layers on a larger area. And based on that, we go and update our CPT program for the next program. adding more CPT data near the locations where we have this sand that's susceptible to liquefaction. We can also run or conduct additional engineering analysis to determine if these potentially liquefiable layers pose a risk to our structure or not, and if we need remedial works. So showing example of each step. So first step, here we are showing this is the black CPT, and these two CPTs are from older program. We can know that from the elevation. So here the elevation was 370, a lift was added to 375, and then CPT was conducted. And then here another lift was added from 375 to 380, and another CPT program was conducted. So these are three CPT traces from three different programs, but they are close to each other within a radius of 100 meters. So first step is to go and look at CPT from the most recent program and check if we have potentially liquefiable layer. In this case, we have a potentially liquefiable zone around elevation 370. Next step would go and look if this is continuous or isolated. So we'd go and look in a radius of 100 meters. We have here the another two CPT traces, and then when we check the continuity of this potentially liquefiable zone, we found that it's not continuous. So the surrounding CPTs confirmed that the potentially liquefiable zone are not extensive, then there's no need for additional CPTs or analysis. Moving to step 3, now we look at the zones that are identified as potentially liquefiable from all the programs, and we see how they are progressing. What's the status of these layers now? Like here from an old program, we have a potentially liquefiable layer around elevation 365. This potentially liquefiable zone was shown to improve with time, maybe from additional compaction or from adding more load on top of it. So now if we look at 365, it has been resolved, it has been improved with time, so no additional CPTs are required. Now, if the extent of the potential liquefiable zones are not discounted by following step 1 to 3, we have to proceed to steps 4 and 5, which are to look at a wider zone and check the continuity of the liquefied sand over a wider zone. We can see here from this example, looking at the wider zone and more CPTs, that the potential liquefiable sand is continuously at a relatively large area. And here, the points marked with red are potentially liquefiable, and we identify that by QT-NCS less than 70 to 80. So we can see here potentially liquefiable throughout a large area. So here we need further investigation. For the next program, we propose new CPTs in the same region. And also we do some more investigations, run some analysis, check if it poses risk to our structure and if we need remedial measures based on case by case. So in general, the track packing of the beaches continues to produce dilated sand, but despite that, in some localized area, the potentially liquefiable sand is continuous. And this is represented by the red and orange dots, as you can see here. By investigating our structure and doing some more engineering analysis, we identified that there's no concern to the stability of the dikes with the current dike configuration, but our dike is being raised again in the future, so we have to keep an eye on those locations. That's why we propose more CPT testing to go in the next program next to those stones, and to confirm or discount the extent of potential liquefiable zone and evaluate if we need more assessment or remediation measures. My last case study here is about a stockpile on Tailings Beach and at an oil sand facility. So here, this is a beach next to a tailings pond as well, and a stockpile was proposed to be placed on the beach. This is the configuration of the stockpile, and it is proposed to be constructed on Tailings Beach, and the beach sand here is not compacted. So the feasibility of the proposed stockpile on Tailings Beach was assessed based on CPT data. So 23 CPT tests with with dissipation test was distributed all over the beach, and the CPT data showed that potentially liquefiable sand covers most of the beach area and is present at various depths. Also, the water table was very high. Showing an example of one CPT on the beach. Here I'm showing the same soil behavior chart. So a lot of the data points fall below this contracted dilative boundary, means that much of our tailings sand are contracted and susceptible to liquefaction. And if we look at the QT-NCS here, we can see many values falling below 70 to 80 QT-NCS. And for the C/P ratio, it is very low. So if we look at the 20th percentile, we are in the range of 0.03, less than 0.05, which are really low values. So we do the same thing. So we collect the data from all the CPTs on the beach and we do some statistics. The 20th percentile of QT-NCS is 43, which means it's well below 70, and our tailings sand are susceptible to liquefaction. Statistics on the C/P ratio for QT-NCS value less than 70 to 80, and our 20th percentile for the C/P ratio is 0.03. Now, if you use these strength parameters in our engineering assessment, we find that the proposed stockpile configuration is not feasible. So it was abandoned because it doesn't work. So the engineering marks here, CPT has become widely used site investigation tool for geotechnical applications, including the oil sands industry. Some of the oil sands applications include profiling, characterization of soft tailings, and evaluation of the liquefaction potential of the tailings sand. While CPT is a powerful geotechnical investigation tool, each site is unique. It has its unique geological and geotechnical condition. And sometimes just one test method is not enough to provide a full comprehensive understanding of the site conditions. And we shouldn't forget that some parameters interpreted from CPT need to be calibrated against other in situ methods in order to represent the actual specific site conditions. And CPT does not provide soil sampling, which may be necessary in some applications. Thank you again for the team members who worked on this work, on this case studies. And here I'm adding the references to the case studies for your interest. I come to the end of my presentation and I'm happy to take your questions.
Okay, thank you very much, Dr. Assile, for this presentation. Now we have the time for some questions. So someone here in the room has any question, please raise your hand. Or in the people in Zoom. Okay, there is a question in Zoom. It says, oh, wait a minute. Is this the same site used in the CANLEX initiative in 1993?
I'm very sorry, I'm not familiar with the CANLEX initiative.
No, that's not.
So,
okay, we have, let me introduce to all of you. We have someone with the project, is Mr. Chad, is here. You can sit here.
Oh, thank you.
He's part of the project as well, so he will help also with some of the answers. So the answer is no, it is not. Any question here in the room?
Hey, Assile, Colin here. Just a quick question about your first case study. Is there any plan for investigation in the future to see how the tailings characteristics have changed after a bit of consolidation in terms of performance?
sorry, so you are asking about 0.5 and if there are more site investigations to come in the future?
Yeah, just to gauge any improvement in the characteristics. Yeah.
Yeah, so actually we have a yearly performance investigation going every year. So we go and we have an extensive both CPT, vein shear, and other in-situ tests, and we keep an eye and we keep monitoring the tailings to check how they are, how their strengths and characteristics are evolving with time.
Okay, great, thanks. So if it's an annual program, I'm assuming then the rate of consolidation after those wick drains have been installed, you kind of have an idea on how that's also accelerated.
Yeah, so looking at the, especially at the lab data and checking the soils content and the SFRs and all these parameters, it gives a good indication on how these tailings are performing and are getting better with time.
Okay, great.
Including consolidation.
Got it, yeah. Okay, well, we'll look forward to a follow-up presentation from you then in the years to come. Any other questions here in the room?
Hi, Assile, this is Levi. I have a general question about flow liquefaction. What's the trigger of flow liquefaction? And do you believe there's a spontaneous collapse of the soil structure, or is it just a strain softening behavior?
So whenever we are designing a structure, if it is a strain softening material, we have to take into account the susceptibility to liquefaction. So yes, strain softening soil. We have to assume that they are prone to liquefaction and run our analysis based on this assumption.
We have a question.
Yeah.
Is there
So just to add on that, the liquefaction can be triggered by strain softening, any change in pore pressure, any change in site conditions that might trigger this strain softening behavior.
Now, the next question is, there is any precaution we're taking the CPT penetration, the membrane and geotextile?
Sorry, again, I didn't get there any precaution. I think that the CPT penetrating the geomembrane, it's really very small area compared to the huge area of the pond. So I don't think there was any repercussions or any harm to the geomembrane, to the intent from the geomembrane.
Great, thank you. Next question. It's a quick question. For the oil sands, if we encounter a lot of layers of potentially liquefiable soil, what remedial measurements are taken?
So I will comment, for example, on the sand dump 8 example. For those zones that were identified as potentially liquefiable, we run some more geotechnical analysis, and based on that, we decide if we need remedial measures, and it is really case by case. So we may go and do some more compaction of the cells, or in some other cases, we look if there is a room to add a buttress, we would go and buttress. So it's really case by case. And as you mentioned, maybe soil improvement techniques may also work.
Any other question here in the room? Okay, so we have last question on Zoom is, do we go for ground? It's a following question from the previous one. Do we go for ground improvement techniques and installation of shield piles walk in these oil sand sites, or are there other techniques to mitigate risks associated with the liquefiable soils?
I not have much experience, but from a personal perspective, given that these projects are are really huge, so ground improvement methods would be very expensive. So I think it would be the last resort or the last remedial measure to resort to. We can first check other measures like further compaction or buttressing or other.
Okay, well, thank you very much, everyone, for coming to the seminar today, and thank you to Dr. Assile for coming on this great presentation. So see you next week with our last seminar for this year. That's all for today. Thank you.
Thank you.